Ahoy shipmates! This is the third lesson of algebraic methods today. So what we've looked at so far is we've seen some algebraic division, polynomial division. We've had a look at the factor theorem, we've proved it and we've used it. And now today what we're going to be moving on to is the concept of algebraic proofs. So you may have done some of this at GCSE, so extending those ideas further. And there's also more than one way of proving something. There's proof by exhaustion, there's proof by deduction, and there are also geometric proofs as well, not to mention proof by counterexample. So we're going to have a look at some of these today, in particular how to prove identities and algebraic expressions. So before we get started, for real as it were, here's 4 warm-up questions for you to try. 1, 2, 3, 4, count them, they're all there. So have a go at those first on your own, and then press play when you want to see the solutions so you can just check you've got them all correct. So let's have a look and talk through the solution together to question 1. So question 1, expand and simplify x squared minus 1 all squared. Okay, even though there's a squared term in here and it's being squared, this is just a general case of expanding out a binomial. So what we do is we just simply square the first term, so x squared squared is x to the power 4. We then multiply the product of these and double it, so x squared multiplied by minus 1 is minus x squared. Double that gives us minus 2 x squared. Finally we square the last term, so minus 1 times minus 1, that gives us plus 1. And the first question is as simple as that. Warm up 2, find in terms of k the discriminant of the following quadratic expression, where k is a constant. So here we just need to remember that the discriminant is given by b squared minus 4ac, where a is the coefficient of the x squared term, so in our case it's k. The b is a coefficient of the x term, which here is 3k. And finally, c is a constant term at the end, which is minus 1. So we just plug those values in. So b squared is k squared, minus 4 multiplied by a, which is k, multiplied by c, which is minus 1. I do apologise, I just spotted again a stupid mistake I've just made. b is not k, b is 3k. Not the best start. Okay. So I'll just alter that there. Apologies for that. I tend to leave my mistakes in unless they're absolutely huge ones, just so you can see that I'm far from being perfect. Being someone that makes mistakes is absolutely fine to an extent. That's my excuse anyway. So 3k all squared, 3 times 3 is 9, k squared is just this, minus 4 times k times minus 1, that ends up being positive 4k. We could factorise it if we wanted. It doesn't really say if we need to or not, so I'm going to leave it like that for question 2. Question 3, write the expression x squared minus 8x plus 17 in the form x plus p brackets all squared plus q, where p and q are integers to be determined. In other words, all it's wanting us to do here is to complete the square. So we take the quadratic expression, which is x squared minus 8x plus 17, and we put into brackets the x, and we half this coefficient of the x here, so half of minus 8 is minus 4. We then square everything. We minus off this term squared, so minus 4 squared is 16, so minus off 16, but then of course you need to remember there was a plus 17 as well. So finally, to simplify, we have x minus 4 all squared, and minus 16 plus 17 overall is plus 1, and then we're done. And so p is minus 4 and q is positive 1. It doesn't say we have to state what p and q are, just write it in this particular form, which we have done, so we don't need to do anything else, and we can move on to the next question. Finally, for the warm-up, We have 2 points, A and B, which are -1, 5 and 4, -6 respectively. For part A, we have to find the gradient of the line segment AB. So we should know now that to find the gradient in between 2 points, we work out the change in y between those points. So we can do -6 minus 5, and then divide that by the change in x between the two same points, which is 4 minus -1. -6 minus 5 is -11, and 4 minus -1 is 5. So the gradient of this one is -11/5. For part B, it says, hence write down the gradient of any line perpendicular to the line segment AB. So any line that's perpendicular to AB will have a gradient of the negative reciprocal of the gradient of AB. So that's kind of gradient -1 over -11/5. So the minuses will cancel, and we have 5/11. So any line perpendicular to AB will have a gradient of 5/11. And then we're done for that warm-up. So now we can move on to the main part of the lesson, which, like I've said before, is about the proofs. So let's have a look at proving some things mathematically. So first of all, we're going to be proving some identities. Now, an identity isn't quite like an equation. An equation might hold true for just one value or two values or several values, but not all. An identity means that one side is exactly equivalent to the other side of this identity symbol, which is like an equal symbol, but has 3 bars rather than 2. So what it means is that one side looks different to the other, but it's literally identical. It's the same thing, just dressed up in a different way. So how do you prove identities? Well, I've got a tip for you, just how to approach the problem generally. So what I would say to do is, when proving it, aim to show that one side, either the left or the right, is exactly the same as the other by manipulating it so it ends up looking exactly the same, showing every single step of your working clearly. Then always make a formal statement of the proof to finish off, just to make it clear that you've proven what needed to be proven. So, looking at this side here, could we factorize it into this? Looks a bit awkward. I'd say expanding out brackets, simplifying and aiming for that would be better. So what I'm going to suggest we do is we take this left-hand side of the equation, expand it, simplify it, and see if it comes out to be the right-hand side. And if we can do that, we've proven it. So what I'm going to suggest we do here is start with the left and make it into the right. So first of all, I'm going to write down just simply LHS. So that's just a lazy shorthand way of saying, let's start with the left-hand side. So x minus 1x cubed. Okay, so I'm starting with the left, which is this. And our target is to expand this out and make it look the same as the right-hand side. So what I'm going to suggest we do first of all is to just rewrite this as one bracket multiplied by itself squared. Then what we can do is we can square out the bracket and then expand it the long way. So x minus 1 over x all squared. So x multiplied by x is x squared. The product of x and minus 1 over x is minus 1. We double that product to give us minus 2. Finally, we take the minus 1 over x and square that to give us positive 1 over x squared. Now what we can do is take the x here and multiply it by everything in turn in the second bracket. So just give yourself enough space for this. So first of all, x multiplied by x squared gives us x cubed. Then x multiplied by minus 2 is minus 2x. And finally for the x multiplied by 1 over x squared, that's going to give us plus 1 over x. Now we do the same for the minus 1 over x. We're going to multiply this by each of the terms in the second bracket in turn. So first of all, we're going to multiply by the x squared, then by the minus 2, and finally to finish by the 1 over x squared. So 1 over x multiplied by x squared, that will give us minus 1 over x times x squared, gives us minus x. Because x squared divided by x gives us an x, but it's a minus. Then minus 1 over x multiplied by minus 2, minus multiplied by minus makes a positive, so we're going to have positive 2 over x there. Finally, minus 1 over x multiplied by 1 over x squared, that's going to give us minus 1 over x cubed. Now we can go about simplifying this and seeing what we have. So first of all, we've got x cubed. We don't have any other x cubed terms, so we can just say we've got 1x cubed. Now let's have a look at the terms involving x. We have minus 2x here and minus x over there, so overall we have minus 3x. Now we can have a look at the 1 over x terms. There's 1 over x here, plus another 2 over x here, so in total 1 over x plus another 2 over x, that's going to give us plus 3 over x. Then we finish off by just noticing there's only one term which is a 1 over x cubed type, which is this, which is a minus. So we've got minus 1 over x cubed. And if you have a look now to what we've got here, it's exactly the same as what's on the right hand side. And so we've proven that this is identical, it's an identity to the right hand side, which is exactly what we wanted to prove. Now I did say make a formal statement of the proof to finish it off. So therefore we can say that x minus 1 over x cubed is one and the same thing as x cubed minus 3x plus 3 over x minus 1 over x cubed. And that finishes it off for us. For the next one, proving quadratic inequalities. So prove that the statement x squared minus 4x plus 5 greater than 0 is true for all real values of x. So when we're proving something, we always need to start from a place which we can get everybody you're trying to prove it to agree with you on. As it stands, this isn't obviously true. So always start off with something which is obviously true. So I've got a tip for you here of how to start off. Okay, so always start your proof from known and completely obvious results and take it from there. So if you're starting from something which is completely obvious, I'm just going to call that a statement of fact, something which is irrefutably true and is beyond any doubt. So what we can do is take this initial statement and jot down workings to manipulate it into an obviously true starting point. When you've done that, then you can work backwards from that to arrive clearly and logically to the statement you needed to prove in the first place. So I'll show you what I mean by this. So if we get our jotting space here, what we can do is take this and manipulate it into something which is obviously true. So we want to end up with this. Our target is this. We need to prove it. Right now it's not obviously true. Now we can find what the minimum value is, and if the minimum value of this is greater than 0, then it's going to be greater than 0 for all x. So how do we find a minimum point of a quadratic? We complete the square. And so what we can do here is complete the square. So x squared minus 4x, put the x into brackets, half this coefficient, which is minus 4, to make minus 2. Square that. Then we minus off this 2 squared bit. So minus 2 all squared is 4. So minus off 4 and plus 5. So let's neaten this up. X minus 2 squared plus 1. This is looking more promising, isn't it? So I'm going to ignore this plus 1 for a moment. And there are sometimes a few ways of approaching this. So you could make a few tweaks to what I'm doing and still get full credit. What I'm going to say here though, if you take anything and square it, what's the minimum value? Well, the minimum value of anything squared is 0. Other than that, anything squared is going to be positive. So what I'm going to start off with here is I'm going to start by saying that x minus 2 all squared is at least 0. So I'm going to start from this here. That's going to be my statement of fact. And what I'm going to do now is I'm going to start from my statement of fact and work in reverse. So eventually I can prove what I wanted to prove in the first place. So if I just put this to one side for a moment, so that's not something you're going to present to the examiner, that's maybe something you could jot down at the side or in pencil, but you're making it clear to the examiner that we're looking in this space here. This is where the proof is going to happen, in this space with the dotted lines. So I'm going to say that x minus 2 all squared is at least 0 for all x. That's completely and utterly obvious to anyone that has any sort of understanding of GCSE maths or beyond. So the next step, if this is true, if that's at least 0, then you can say that x minus 2 all squared, if I add 1 to both sides, or just add 1 here, if it was at least 0 before, it's definitely greater than 0 now. So I'm going to take this and expand it out. So x squared minus 4x plus 4 plus 1 is greater than 0. Just by expanding this out, I've got the plus 1. And if I simplify this down now, I arrive at x squared minus 4x plus 4 plus 1 is plus 5 is greater than 0 for all x. And that little square symbol, you'll see sometimes, that's just a way of saying the proof's done, it's finished off. So I've concluded with a final statement of the proof, saying therefore, look, we've done it, we've proved it, job done. Question 3, deductive proofs. Deduction means just starting from something which is known and building step by step logically. So for question 3, we have an equation kx squared plus 2kx minus 1 equal to 0. K is a constant. We're told it has no real roots. We need to prove that k satisfies the inequality that k is greater than minus 1 but less than or equal to 0. and so deductive proofs or known facts. Well, what known facts, what do we know about a quadratic that has no roots? So this is just harking back to some revision on quadratics. This is about the discriminant. So what we can say first of all is no real roots, therefore the discriminant of this quadratic function must be less than 0. So based off that, we can work out what discriminant actually is. Discriminant's b squared minus 4ac. So what's a, what's b, and what's c? A is the coefficient of x squared, which is k. B is the coefficient of x, which we can see as 2k, and c is the constant term at the end, which is minus 1. So if we plug in these values into this, b squared is 2k squared minus 4 times k times minus 1 must be less than 0. 2k all squared is 4k squared. Minus 4 times k times minus 1, that's positive 4k. We can divide both sides by 4 to give us k squared plus k is less than 0. Then let's factorise. We get k brackets k plus 1 is less than 0. So what we can do from this here, so we've got to this stage, great, but we're not quite done yet. So what we could do is actually sketch a graph to make it clear what range of k we're interested in. And so if I were to plot k versus k brackets k plus 1, we can see the critical values where it's going to be equal to 0 are when k is 0 or minus 1. So it's going to be a positive quadratic because this is k squared plus k, positive k squared. So it's going to cross the k-axis, as it were, at 0 and minus 1. So it's going to look something like this. And we're wanting this to be less than 0. So we're wanting it to be at this region here. So in other words, we want it to be between minus 1 and 0. So therefore, k satisfies this inequality, which is almost the same as what we wanted to prove, but just be careful. This is almost a trick question, really. This inequality symbol here means that we're allowing k to equal 0. So let's just inspect what happens when k equals 0. So when k equals 0, this here, k squared plus 2kx minus 1 equals 0, that becomes, it reduces down to minus 1 equal to 0, which has no roots also. So also has no solutions. So with proof, you need to be really clear and cover every single case. If you left it like this, you'd drop a mark. You need to think about what if k were equal to 0. So k has to be between minus 1 and 0, but we've just checked that when k is actually equal to 0, that holds and doesn't allow this to have any roots, because if k equals 0, we have a nonsense anyway. And so if we allow k to be 0, that's fine, because that wouldn't give it any roots either. So therefore, we can go slightly better than this and say that minus 1 k 0 like this. So a slight extra inspection and we're done. You're nearly done at this step, but just be really careful that you've covered every single possibility. So this extra step is crucial. Last one to look at is a geometric proof. So proving geometric statements from known facts or definitions. So we're asked here to prove that the quadrilateral A, B, C, D with different coordinate points given is a parallelogram. So where to start with this one? What you need to do, if it's a geometric proof involving a shape, recall what the minimum necessary conditions are for a shape to be a parallelogram. So what makes a parallelogram in its simplest way? Have a think, and hopefully you'll agree with me that to make a shape a parallelogram, for it to be a parallelogram, all we need to have is two pairs of parallel sides. So if we can prove that AB and CD are parallel, and also BC and AD are parallel, or whatever, we've proven it. So we just need to prove two pairs are parallel to one another. But which pairs are we going to pick? So the second step I would advise strongly is that we do a sketch of this parallelogram so we can see what sides are likely to be parallel to each other, so we're not needlessly wasting our time trying every single combination of these letters. So whereabouts to start? I'd imagine reading from left to right like a book. So what's the leftmost point? Which point would come first? -3, 3, 2, D would come first, wouldn't it? That's the furthest to the left. So D, we can just put down anywhere. We don't need to necessarily do an XY coordinate grid. We can just do them in relation to each other. After D would be A, because -3 is slightly over from D, and 3 is higher than 1. So A is going to be up here somewhere. So we can label this on now for A. A is going to be up here. Now if you notice, after labeling on A, C is at the same height as A, because C has the same Y coordinate, but C is 5 units along. So we can jot in C afterwards. I've popped in B here, which is 3, 5, but C would be 2, 3, which is somewhere along, which is next to A. So we've got something that looks like this. So we can see now, hopefully, which two sides are likely to be parallel. So what I'm suggesting, just using a sketch, is we can check the gradient of AD and BC, see if they're parallel, and also check the gradient of AB and CD, and see if they're parallel to each other. And if we can do that, and if that works, when we've proven it has to be a parallelogram. So let's first of all go for the gradient of AB. So the gradient of AB is a change in y between A and B. So from 5 to 3, that's 5 minus 3. For change in x, 3 minus minus 3. So let's simplify that. 5 minus 3 is 2. 3 minus minus 3 is 6. So the gradient of AB is a third. Let's try now the gradient of CD. So C is 3 at y, D is 1 for the y coordinate. So 3 minus 1 is a change in y. Change in x is 2 minus minus 4. 3 minus 1 is 2. 2 minus minus 4 is positive 6. That simplifies down to 1/3. So we can see here that AB is parallel to CD. So I'll call that 1. So that's one pair of parallel sides. We need to check as well that we have another pair of parallel sides. So let's now look at AD. So what's the gradient of AD? The change in y from D up to A is 3 minus 1. The change in x is minus 3 minus minus 4. So 3 minus 1 is 2. Minus 3 minus minus 4 is minus 3 plus 4, which is 1. 2 over 1 is 2. Finally, let's look at the gradient of BC. So between B and C, the change in y is 5 minus 3. And the change in x is 3 minus 2. 5 minus 3 is 2. 3 minus 2 is 1. 2 over 1 is 2. So therefore, from these two, we can see that AD is parallel to BC. I'll call that 2. So let's think of this now. So from all of above, we can say that from 1 and 2, we can see that ABCD has 2 pairs of parallel sides. So therefore, it's got to be that ABCD is a parallelogram. There's no other two ways about it. If you've got 2 pairs of parallel sides, if you've got a closed shape, ABCD, it's got to be a parallelogram. It sorts out as well that the lengths of the sides have to be the same, because if this side length was different, for example, that would force this one higher, and then it wouldn't be parallel. So this is the most succinct way of proving a parallelogram is a parallelogram. So we've done it. Now it's up to you to try some on your own. So if you go to exercise 7D, starting on page 149, try questions 2 through to question 6, and then 11 through to 19. That'll give you a good grounding in the basics of this proof idea. You might find this hard at first because it'll be fairly new to you, but the idea is to never give up. So try and check your answers straight away. If you're struggling, let me know, or drop me an email. Keep plugging away, keep working hard, and I'll see you all soon. Thanks again for listening.